Structural Analysis 2, Chapter 8, Deflections using Energy Methods. Let's solve an example in frames. So we want to determine the horizontal displacement at C, at support C. If we do know moment of inertia is provided like 600 h to the force, and it's made of 836 steel with the units of elasticity of 29,000 ksi. So that turns it to like 29,000 psi. So we do have a ruler, have a ball support like cy. We do have ay and like ax, and in our frame, in the vertical part of our frame, a distributed load of by intensity of 4 kilopound over feet applied at the length of 10 feet of AB, and the other part is C by the length of 8 feet. We want to calculate the horizontal displacement of support at C. Let's see how we can approach our problem. So if this is our main problem, if we apply the virtual work method by applying a 1K, 1 unit force, we can simply solve it from by virtual force, virtual work method. 1 times delta C horizontal is equal to integration of small m capital M x over y. So definitely we have two parts. So if we call this one part 1 and the horizontal member like part 2, we need to calculate a small m capital M for the first part, and again small m capital M part B, then multiply each part, and by effect of superposition add them up together and resolve like delta C horizontal. Let's see how we can approach our problem. So first of all, if we want to get the support, first of all converting this distributed load to a concentrated at the center. So then summation of moment about any arbitrary point can consider point A, because it just simply eliminates two forces of AX and AY comparison to C. So it just gives us a CY equal positive 25, and if a CY is 25 in positive Y direction, it just simply gives us AY. Should cancel out that force, so that's a downward force, and all the horizontal force, which is 40, should be cancelled out by AX, the opposite direction. As soon as we have all the forces, we can plug our section through, for example, part A and B, part 1 and part 2, vertical member, horizontal member, to get the real moment. So if we cut the section like by a length of x1 and get the moment equation, if we cut our structure through, just get the moment, it just gives us mx1 is equal to this equation. And if we just cut our section like beam at a distance of x2, we can get mx2, that's a equal to 25 x2 is our real moment, because we didn't change any format of forces in our real structure. And if you just all the forces from our structure and just applying a 1K unit force at the horizontal direction of ball C, support C, we can get the mutual moment effect for both of them. First of all, we can get the reaction, it just gives us a cy is equal to 1 point cy is 1.5, ay is at the 1.5 downward, and easily see that. And also if this is 1k horizontal, at a there is 1k alt bar. That's the summation of fx and summation of fy in my 2D space. As soon as we have that, we can cut the section through by creating mx for first part, that's mx1 is equal to x1. So it just gives you mx2, which summation of moment about x2 goes 0. It just gives you mx2 is equal to 1.25. So the previous part we had m capital X1. Here we got m small m x1, which is virtual one, and also small m x2, which is these two equations. So we have both a virtual moment and real moment for both parts. So if we just go by the equation of virtual board, that's integration through 0 to L m x m small m capital M dx over ei. And for example, if this is our real moment, we have real moment for first piece, real moment for part 2, also virtual moment part 1, and virtual moment part 2, which is here. As soon as we replace that in our equation, so it just says for the mx1 small m times capital M x1, so it just comes from here, mx1 times small m times capital M, just small m x1 times capital M, then from 0 to L, because this length from A to B, which is equal to 10 feet. As you can see here, this vertical distance is 10, plus a integration from 0 to 8, which is from B to C, that's 8 feet. As you can see here, that's 8 feet from 0 to 8. Small m, which is 1.5 over mx2 small m, and capital M, which is 25x2. And if you do so, it just gives you delta C horizontal is equal to almost 8,000 over EI plus 5,000. So this is the result of this part, and this is the result of this part. Add them up together, it just gives you delta CH is equal to 13,666.7. The unit for numerator is kilopound feet cubed over EI. If you cancel out the unit from numerator and denominator, it's either in terms of feet, inches, in USCS customary, meter, and millimeters in SI units. So let's complete our solution. We have everything. We had the solution like in parametric, and let's replace our numeric value to get the amount of horizontal movement of support at C. So delta CH is equal to this term, and if you just replace EI from the top and convert the inches to feet or feet to inches, you can easily get this amount of delta C horizontal is equal to 0.113 feet, 1.36 inches, and each 12 inches is 1 feet. 1 foot. Thank you. Next video we'll solve this problem with a graphical method, which is far simpler than the integration, but you're allowed to use either of them for calculation of vertical displacement with visual. Thank you.